So in this problem, we are going to find an equation for a tangent plane. Now, before we even really get started, I want you to look at the equation of the surface that we are given. Z e to the x plus e to the z plus 1 equals xy plus y minus 8. Now that looks pretty gnarly, and more specifically, it is going to be difficult, if not impossible, to solve for z. Okay, so in other words, it's going to be very, very difficult, if not impossible, to write the equation for this surface in an equivalent form that looks like z equals some kind of expression in terms of x and y. The reason I'm bringing this up is that we have two methods for finding an equation for the tangent plane, okay? And the first one, the one that we did back at the beginning of this unit, involved or required us to have an equation for the surface in the form z equals some expression in terms of x and y, or f of xy equals some expression in terms of x and y, and we just can't do that here, which means that we need to resort to tangent plane method number 2. And tangent plane method number 2 focuses on the fact that the equation of our surface, which I've rewritten below in red as z e to the x plus e to the z plus 1 minus xy minus y equals negative 8, is a level surface of a function capital F of 3 variables. So a level surface you can think of as the analog of a level curve, but with one added dimension. So functions of 3 variables have level surfaces, whereas functions of 2 variables, as we've seen, have level curves. They are the same kind of object. They're the same kind of entity. For a level curve, we're saying, hey, what are all the points x, y, such that the function value is, I don't know, 2, for example. Okay, but a level surface is what are all the points in space x, y, z, such that the function value capital F, in this case we're calling it capital F, has a function value of negative 8. So we call it a level surface. Now, why would we do that? At first glance, it might seem counterproductive, or like we're making the problem even more complicated. Well, the answer is that the gradient vector at the point in question, which I just realized I forgot to write up at the beginning of the problem, 0, 8, negative 1, the gradient vector at the point 0, 8, negative 1 is perpendicular to the level surface containing this point, which in turn means that the gradient vector at 0, 8, negative 1 is perpendicular to the tangent plane, the plane tangent to this surface at 0, 8, negative 1. Now, it might be starting to crystallize for you. Why do we care about this? Well, it turns out when we are trying to find an equation for a plane, if we have a vector, if we know a vector that is perpendicular to that plane, called the normal vector, then pretty much everything falls right out from there. That gives us everything that we need. That unlocks the equation of the tangent plane. So essentially, the reason why we're framing this as a question of level surfaces and gradient vectors is that the gradient vector at 0, 8, negative 1 is our normal vector. And this is very good news because the gradient vector is very easy to compute. Or maybe I shouldn't say easy because it is a bit tedious, but it's well understood. It's just the vector whose components are the partial derivatives. So to find our normal vector, the vector normal to this plane, this tangent plane that we're trying to find, the key to finding it is simply to find the 3 partial derivatives of this function here. And because I'm a kind and benevolent instructor who's also looking to shave a few minutes off the time of this video, here are the partial derivatives. Plus, you all are already very, very good at partial derivatives. So anyways, there we go. There is the generic formula for the gradient vector. Now we need to find the specific gradient vector at the point 0, 8, negative 1. So again, behind the scenes, I'm going to try to save some time and do some basic computations for you. I would, of course, recommend, as always, that you go back and fill in the blanks yourself. The gradient vector that we get here is -9, 1, and 2. So this is our normal vector. This is the vector that is normal to the tangent plane. And so what this gives us is that we know that the equation, the coefficients in the equation of the tangent plane match the components of the gradient vector. To see why this is, you're going to need to go back to the original lesson. We're just going to take it for granted right now. So the equation of the tangent plane is of the form -9x minus y plus 2z is equal to, well, sorry, we're not quite done yet. It's equal to something. You're probably thinking, Dr. Cook, can you do a little bit better than that? Can you do a little bit better than something? And I'm glad you asked, because the answer is yes. How can we figure out what goes on the right-hand side? Well, what do we know about this tangent plane? Well, we know that it passes through the point 0, 8, -1. Right? And what that means is if we plug in 0 for x and 8 for y and -1 for z, then the equation should be balanced. The left-hand side should be equal to the right-hand side. So how can we figure out what goes on the right-hand side? Well, we can just plug in x is equal to 0, y is equal to 8, and z is equal to -1. Let's try it and see what happens. -9 times 0 minus 8 plus 2 times -1. Okay, so what does this equal? My arithmetic skills are a little bit rusty, but I believe that equals -10. So that must be our something here on the right-hand side. In order for this to make sense, right, in order for the point 0, 8, -1 to be in this tangent plane, to be contained in this plane, well, then the point must satisfy the equation of the plane. That's sort of the whole point of an equation, remember? It's to give us a criterion that we can use to judge, hey, which points are in this plane or on this curve or part of this object and which aren't. So anyways, to wrap up, this is the equation of the plane that is tangent to the surface with this equation at the point 0, 8, -1. This was what we call tangent plane method number 2. Really quickly, we used that because it would have been very, very difficult to take this equation of the surface that we were given and solve for it in terms of z, which is an ingredient that we need to use tangent plane method number 1. The main idea here is that we express our surface as a level surface of some function of 3 variables, and then we use the result that the gradient vector is perpendicular to level curves / level surfaces, which means essentially that the gradient vector of our function capital F here can serve as the normal vector for the tangent plane. And if you have the normal vector, a vector that is normal to a plane, then you can find the equation for that plane very, very easily. Anyways, that is the end of this problem.